Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be looking at some examples of using mole ratios and a before change after table to make predictions of the amounts present in three chemical reactions. Okay, so you've got a sheet where it's got these three listed on it, so do your best to follow along and complete as we go. Okay, so the first one is we're saying that lead metal is reacting with hydrochloric acid, HCl, to form lead chloride and hydrogen gas. How much hydrochloric acid is needed if we have 4 moles of lead? Okay, so as ever, we must start with a balanced chemical equation. So we've got lead solid reacting with hydrochloric acid to form lead 2 chloride, which is PbCl2 plus hydrogen gas. Okay, now looking at this, in order to make it balanced, I need to have a coefficient of 2 in front of my HCl. Okay, so I'm being asked, all right, if I have 4 moles of lead, okay, and then a certain amount of hydrochloric acid, okay, then and I'm starting with 0 product. Now, one thing that I'm going to do, and we're going to do in these examples to make things easier to start with, is that we're going to consider that we've got a certain number of one reactant, and then we have an excess. We have an excess amount of the other reactant. Okay, so I'm going to use a little XS symbol, not because I'm clever, but because I want to keep it short, to indicate that we have more than enough hydrochloric acid to react with our lead. Okay, now so what we can identify here is that all of the lead metal is going to react. So I'm losing all 4 moles of lead metal to form 0 moles of lead left over. Okay, now even though the question is not asking me to do this, I'm going to complete this side of the periodic the before change after table. Okay, so if I lose, or if this decreases by 4 moles, I can look at my ratio of this and I see that I've got a ratio of 1 to 2 to 1 to 1. So for every 1 mole of lead that reacts, 1 mole of lead chloride forms, which means 4 moles of lead reacting forms 4 moles of lead chloride and also 4 moles of hydrogen gas. So I end up with 4 moles of each at the end of the reaction. Okay, but now I can say, all right, I've got an excess, but some of those moles will be involved in the reaction. Okay, so I've got a ratio of 1 to 2 here. I use up twice as many moles of hydrochloric acid as I have lead. So if I'm using up 4 moles here, then I'm going to use up 8 moles here. Okay, now I still have an excess, an unspecified amount more than I need, but I can then say, therefore, 8 moles of HCl is required. Okay, so I'm going through the process, doing my calculations, but it's important that you can make a summing up statement at the end depending on what the question is actually asking from you. Okay, let's move on to the second example. Okay, so here's our second example involving calcium hydride reacting with water to form calcium hydroxide and hydrogen gas. So we're asking if 2.5 moles of calcium hydride, if that's what we have, how many moles of hydrogen gas will we form? Okay, so this is what we're trying to find. Okay, so I'm starting with 2.5 moles of calcium hydride, and I'm again going to assume I have an excess of water. Okay, and I also have 0 moles of both products to start with. Okay, I'm using up all 2.5 moles of my calcium hydride to form, so to have none left over. And I'm also still going to have an excess of water remaining. Okay, looking at my reaction, looking at my ratio where I've got 1 to 2 to 1 to 2. Okay, so for every 1 mole of calcium hydride that reacts, I need 2 moles of water. So 2.5 moles of this means I need 5 moles of that. Looking at my ratio here, that for every mole of calcium hydride that reacts, I produce 1 mole of calcium hydroxide. So this increases by 2.5. And then for every 1 mole of this that reacts, I produce 2 moles of hydrogen gas. So I produce 5 moles of gas to leave 5 moles at the other end. So therefore, 5 moles of H2 is produced. Okay, remember that you must end up answering the question as it's asked. You can't just put in data into the table and then just assume that that stands for itself. You need to use it as a tool in order to complete the question. Okay, it's just like creating graphs in maths, or graphing mass versus volume to look at density. Okay, it is a tool, it is a technique, but that it is a means to an end. Now, you also aren't, it's not mandatory that you must use a table like this, but it's a super helpful way to keep track of the different substances in a chemical change. Okay, so you won't necessarily be, expected to use one in the HSC, but certainly you will find it a very useful tool to get used to. Okay, let's have a look at our third example. Okay, so looking at example number 3, so we've got this reaction occurring here. This substance is known as benzene. Just as out of curiosity, we're saying, all right, well, how many moles of water will be produced if 0.45 moles of oxygen gas is reacting? Okay, so we start by filling in our before line, remembering that we have 0 product to start with, and then we're also going to be assuming that we're using up all of our oxygen. Okay, so we're using up all 0.45 moles of oxygen to leave none left over. Now, the reason that this one gets a little bit more complicated is that our ratios are not quite as neat. We have a ratio of 2 to 15 to 12 to 6. Okay, so there has to be a little bit more careful calculation involved here to get the answer that we're after. Now, we're assuming at this point, because it's not specified, that we have an excess of our benzene, our C6H6. And then we are still going to have an excess remaining at the other end, that we still have some left over. Okay, but so now we have to look at our ratios carefully to work out how much other things are increasing or decreasing by. Okay, so the moles of our C6H6, we have a ratio of 2 moles of C6H6 for every 15 moles of O2. Okay, so we would multiply that by our 0.45 moles of O2 to work out exactly how much is going to be reacting. So we're decreasing by 0.06 moles. Well, that's how many moles of C6H6 is required. Okay, so we still have an excess, but that's how much it's changed by. And now we go through the similar sort of process to look at our carbon dioxide and then our water. Okay, so I'm going to continue to use this little space over here as a bit of a canvas. Okay, so we have, now what's probably easiest to work with now is that I've got some simpler ratios from the C6H6 to the others. Now, the great thing about using mole ratios is that you can compare any one substance to any other substance in your reaction. Okay, it's still a matter of comparing the coefficients. Okay, so whereas the 15 and is not an odd number, whereas the others are even. So where I'm going to go with something, pick something simpler. So I have 12 moles of carbon dioxide for every 2 moles of C6H6. So I'm going to multiply that by our 0.06 moles. Okay, so I get 0.36 moles of CO2. So this is going to increase. Ooh, be careful not to make a silly typo like I just about did. So we end up with 0.36 moles of carbon dioxide. Okay, and then I've also got, I have 6 moles of water for every 2 moles of C6H6. Okay, so I get 0.18. Okay, so therefore 0.18 moles of water will form. Okay, so I realize that there's not great contrast there. You're kind of in a bit of a glossy bit. Hopefully you can see that now. Okay, now the other thing you can do in looking at this, or even just kind of mentally, you can make it a little bit simpler and say, all right, well, 12 over 2 is the same as a ratio of 6 to 1. So you could just multiply this by the 6 over 1 instead. 6 over 2 is the same as 3 over 1, so you're just multiplying this by 3. Okay, and so you can use that approach to get you the answer that you're after. Now, you notice that I did fill out the complete table, even though I wasn't actually didn't need to know every one of those values to answer the question. I only needed to be able to relate from here to here. And I could have done that straight away without filling in anything else. I just wanted to be able to demonstrate to you to help you consolidate how you do this process. Okay? And it's good to be able to get it complete so that you can show that as someone else who is looking, like myself, that you get how this process works, that you know how to compare mole ratios and look at moles of any substance in that reaction. Okay, not just as the path of least resistance to the answer. Okay, thanks very much for watching. Bye for now.